Lepton family. This includes electrons, muons and neutrinos. So which interactions involving leptons do you already know about? Well, we've already looked at some Feynman diagrams to explain these. So the first one is our neutron-neutrino interaction here. So we get a W minus exchange particle, and that results in the transfer of negative charge from the neutron, which leaves a positively charged proton and an electron or beta minus particle. Second one is proton antineutrino interaction. This time we have a W plus boson transferring the charge, and that results in a neutron and a positron or a beta plus. And one of the other ones we looked at was the proton capturing an electron from the inner shell, and this time again we have a W plus boson which leaves a neutron, and then we get a neutrino. So some particle interactions are observed and some particle interactions are not observed. And what physicists do is they make up rules that fit with observed interactions and that are broken with non-observed interactions. For example, what we have here is a neutron plus a neutrino going to an antiproton plus a positron. And if we thought about the mass, well, neutron and a neutrino, okay, proton, one antiproton and a positron, mass seems okay here. And if we look at the charge, well, we start off with no charge, and then we've got an antiproton which is negative, and we've got a positron which is positive, so that makes no charge. So it seems that the charge is conserved as well. But this interaction actually does not happen. It's not observed. So what physicists have done is they've set up rules, as I just said. And the first set of rules that we're going to look at are the lepton rules. So each particle has what we call a lepton number. All lepton particles have a lepton number of 1. Any antileptons have a lepton number of -1, and all non-leptons have a lepton number of 0. And if you look at the bottom here, the lepton number is conserved in any interaction. So before and after will be the same. So let's have a look at these two interactions. You've got a neutron and a neutrino. So neutron is not a lepton, so the lepton number, and we'll have an L over here to show lepton number, is 0, and neutrino is a lepton, so that's got a lepton number of 1. Proton is not a lepton, and electron is. So therefore, it's conserved. Second one. Neutron and neutrino going to antiproton and a positron, which is the one we just looked at. Lepton number neutron 0, neutrino 1. Antiproton is still 0 because it's a not a lepton. And we've got a positron, which is an anti-electron, is -1. So this time the lepton number is not conserved, and this interaction is not observed. Let's have a look at this muon decay. So we have a muon, which is a lepton. We've got an electron, which is a lepton. We've got a muon neutrino, which is a lepton. And we've got an electron antineutrino, which is -1, because it's an antiparticle, an antilepton. So these two cancel each other out, and we're left with 1 and 1, which is fine. Let's have a look at this interaction. Can a muon decay into a muon antineutrino? So, well, charge-wise, we've got -1, we've got -1, we've got 0, 0, because these are neutrinos. So charge works, and charge we normally have with the symbol Q. But let's have a look at the lepton number. So a muon is a lepton, an electron is a lepton, an anti-muon neutrino, or a muon antineutrino, has -1, and electron antineutrino is -1. So we're ending up with 1 and -1. So this interaction is not observed. Now there's one last issue with, and this is muon decay again. Can this interaction happen? Well, let's have a look at charge. We've got muon, which is negative, electron negative, and we've got neutrinos, which are neutral. So charge looks okay. Let's have a look at the lepton number, L. We've got a lepton, yep. We've got an electron, we've got an electron neutrino, we've got a muon antineutrino, which is -1. Those cancel out, leaves 1 and 1, so that looks fine. But actually this interaction cannot exist, it doesn't happen. The reason being that a muon can only decay into a muon neutrino. It can't decay into a muon antineutrino. And also an electron can only be created with an electron antineutrino. So what we have to do in this case, and in fact if you see a muon decay, you should apply this scenario, is we look at the lepton number for electrons and the lepton number for muons. So if it is an electron or an electron neutrino, it has an electron lepton number. If it's a muon or a muon neutrino, it has a muon lepton number. So let's try this one. So muon is not an electron. Then we have electron, we have electron neutrino, and we have a muon antineutrino. So this already shows that this interaction cannot happen. And if we look at the muon lepton number, it is a muon, electron isn't a muon, electron neutrino isn't a muon, or anything to do with a muon. And a muon antineutrino is -1, so that also shows that this cannot exist. So if you have muon decay, you need to split up your lepton numbers into electron lepton numbers and muon lepton numbers. If it's something to do with an electron, it will have an electron number, lepton number. And if it's something to do with muon, like a muon neutrino or an muon antineutrino, then it would have a muon lepton number. This is all on page 23 in your book. Thank you.